The focus of this video will be the normal curve and its connection with z-scores. We'll also review how to calculate a z-score and how to find area under the curve using z-scores. We'll start by briefly reviewing the normal curve. The normal curve looks approximately like the shape you see here, that bell shape. We see the mode, median, and mean are all the same number, and they're represented by the center of the curve. That the left and right side of the curve, that means either side of the mean, median, mode line, are symmetrical, and that the tails, both the lower tail and the upper tail, are asymptotic. As you know, the y-axis and thus the height of the curve corresponds to the frequency of the raw scores, so we can just focus on what's going on the x-axis. As we noted, the mode, median, and mean are at the center of the graph, so I've got the symbol here for a sample mean presented at the middle of our curve. As we move out, we move in standard deviations from the center of the curve. We can move one standard deviation out, that's the mean, plus one standard deviation above, or one standard deviation below, that's the mean minus one standard deviation. This gives us the range where we expect a lot of scores to be. A little over 2/3 of scores are expected to be in this range. Specifically, it's 68.26% of scores that are expected to be from one standard deviation below the mean to one standard deviation above the mean. To locate any other of the movements along the x-axis, we just continue adding one standard deviation for the first section, two standard deviations for the second, three standard deviations for the third, and we could theoretically keep going on endlessly because of the asymptotic nature of those tails. The same thing applies to moving to the left side of the mean by moving one standard deviation below the mean, two standard deviations below the mean, three standard deviations below the mean, and theoretically on to infinity in the negative. Let's say we had a quantitative variable with a mean of 20 and a standard deviation of 3. That would mean that the graph stays exactly as it's drawn. The only thing we're going to change is what's written underneath the graph on the x-axis. So I would drop the mean at the center, mean is 20. Then I would add one standard deviation to get the movement one standard deviation above, that's 20 plus 3, or 23. And I would subtract one standard deviation to get the movement that's one standard deviation below. 20 minus 3 gives me 17. And then moving to the left, I'm subtracting. So I have scores of 17, then 14, then 11. This you should already be familiar with, but what we'll focus on here is what this means in regard to the likelihood of these scores. Let's choose the mean as a starting point. Theoretically, half of the raw scores appear to the left of the mean, and half of the raw scores appear to the right of the mean. That's because the mean is the center line that splits the curve in half. There are a few things that we presume to be true when we use the normal curve. One of those is that 68.26% of the scores are within one standard deviation of the mean. That's because 34.13% of scores are expected to be from one standard deviation below the mean to the mean. An additional 34.13% are expected to be from the mean to one standard deviation above the mean. When we add these two proportions together, we get that 68.26% in the middle. So approximately 2/3 of scores, when data are normal, are expected to be from one standard deviation below the mean to one standard deviation above the mean. You'll notice that as we move further away from the mean or further away from the center, that the curve is getting shorter and shorter. That means that the corresponding percentages as we move away from the mean are getting smaller and smaller. Let's start by looking at this orange piece. That's from one standard deviation above the mean to two standard deviations above the mean. This area corresponds to 13.59% of the total area under the curve. With that in mind, let's look at the white piece on the left. This corresponds to being from one standard deviation below the mean to two standard deviations below the mean. This area is also 13.59%. The reason for this is because our graph is symmetrical. So as the right side descends, the left side descends in the same pattern. So pause for a minute and think about what percentage of the curve falls from two standard deviations below the mean to two standard deviations above the mean. You should be getting that it's 95.44%. The way we get this is by adding the 13.59 plus the 34.13 plus the other 34.13 plus that last 13.59. Another way you could do this is adding the 13.59 and the 34.13 from either side and multiplying it by 2 because this is a mirror image. If we go from 2 standard deviations above the mean to 3 standard deviations above the mean, our percentage shrinks even more and is now approximately 2.15%. That means the corresponding segment on the other side of our graph, that's from 2 standard deviations below the mean to 3 standard deviations below the mean, will also correspond to 2.15%. I want to point out here that you'll sometimes see in graphs and tables online or in other sources or textbooks that these segments are noted as 2.14%. We're going to use 2.15. It's a rounding difference and where folks are setting their cutoff, and it's okay if you put 2.14 here because you'll see that a lot as an accepted answer in resources, but we'll stick with the 2.15. This leaves only about 0.13% for each of our remaining tails. That's from going from 3 standard deviations above the mean out to positive infinity, and from 3 standard deviations below the mean out to positive infinity. Also, if you look on resources online and some other textbooks, they might call this area 0.14. That's if they use the 2.14 cutoff for those 2 green segments, but we're going to stick with the 0.13 for our lesson. At this point, you may be wondering where these percentages came from. Well, these are largely coming from nature. When we see things that are normally distributed in nature, we tend to see this kind of pattern emerge in our data. This has also been demonstrated by random number generators, where we give it a standard mean and ask it to normalize the data. So in that, we're kind of artificially making this true. But in general, we presume this to be true because it has been observed many times before in various studies and in various variables in nature that are quantitative. So for our purposes, we're going to be diving less into why are these the percentages that are used, and instead we're going to focus on how to use these percentages. Take a moment here to get acquainted with these percentages by doing some addition. For instance, let's add again those segments that are at the center. When we do that, we get 68.26%. We expect about 68.26% of raw scores for any normal quantitative variable to fall from 1 standard deviation below the mean to 1 standard deviation above the mean. We also know that about 95.44% of scores are expected to fall from 2 standard deviations below the mean to 2 standard deviations above the mean, because we can simply add the 13.59 plus the 34.13 plus the other 34.13 plus the 13.59. So what percentage of scores fall from all of the identified areas here in the curve? You should be getting 100%. If I add 0.13 plus 2.15 plus 13.59 plus 34.13, I get 50%. And that corresponds to both the bottom half and also the top half, because this is split down the middle into the 50% lower scores and the 50% higher scores. Let's try one that's a little more complicated. Let's say I want to know what percentage of folks are from 1 standard deviation above the mean to 3 standard deviations above the mean. In this case, I'm looking for a different segment. I'm looking for the area that goes from this line here, 1 SD above, to this line here, 3 SDs above. This full area can be found by adding the 13.59 plus the 2.15. When I add these areas, I get a total of 15.74. If we change this up slightly and ask what percentage is between 1 standard deviation below the mean and 3 standard deviations below the mean, well, now I've identified a new area from 1 below to 3 below, and I'm trying to find this segment. I follow the exact same steps. I would add the 13.59 and the 2.15, and I would find this area is also equal to 15.74%. That's because the graph is symmetrical, and this is the corresponding negative side area for the one we found on the positive side just a moment ago. Now we'll try it again by converting our raw scores to Z-scores. Assume we have quantitative data which are normally distributed, wherein the mean is 100 and the standard deviation is 10. On your own scratch paper, try filling in the x-axis with all of the numbers corresponding to z's of -3 to z's of +3. Take note here that we typically sketch our graph going from -3z to +3z because almost 100% of scores are expected to be within that z-score range. I start by putting my mean at the middle, and then I'm going to add 1 standard deviation each time I move to the left or to the right of the mean. So that gives me 110, 120, and 130 in this case as I move to the upper end or to the right side of the mean, and 90, 80, and 70 as I move to the lower end or left side of my graph. I'm also going to fill in the percentages that I already know about. Now that I've drawn those in, I'm ready to think about the areas under the curve. Let's say I wanted to know what percentage of scores in this variable's data set would fall from 90 to 80. That means I want to know what percentage of folks were expected to have a raw score between 80 or 90. I can see that that area would be 13.59%. How about if I wanted to know what percentage of folks were expected to have a raw score between 110 and 120? I can easily see here that that area is also 13.59%. That's the same thing as asking what percentage of scores are expected to be from a z-score of 1 to a z-score of 2. Pause here to find what percent of raw scores are expected to be between 70 and 80. You should have gotten an answer of 2.15. Notice that that's the same percent of scores that would be from 120 to 130. That's because a score of 80 to 70 represents movements from 2 SDs away from the mean to 3 SDs away from the mean on the negative side, and scores of 120 to 130 in raw correspond to movements from 2 standard deviations above the mean to 3 standard deviations above the mean on the positive side of the graph. Let's try a more complex one. Pause here and try to find what percentage of scores are between raw scores of 90 and 120. To do this, I recommend the 3-step method: sketch, shade, then draw. We've already sketched our curve, so let's shade the area we're interested in. We want to know the area that corresponds to a raw from 90 to 120. So I'm looking for all of the area between those two numbers here on my graph. When I sketched and shaded, I can see that this area is going to be a pretty large segment of my graph. Now I can easily identify what percentages I need to use. I've got this segment here of 34.13, another such segment of 34.13, and this last segment of 13.59. So to find the total percent, I simply need to add these up. When I do that, I get 81.85%. That means the percentage that corresponds to a z-score from -1 to 2 is also 81.59 because the raw scores correspond to specific z-scores. Now try it again with these two new raw scores of 70 and 120. Find the percentage of area that corresponds to scores between 70 and 120 using the sketch, shade, and solve method. We already had a sketch, so I've just shaded it. Now I'm going to move on to step 3, which is solve. I see that I've got 2.15, 13.59, 34.13, another 34.13, and another 13.59. I'm going to add all these together to get the total area shaded under my curve. When I add this, I get 97.59%. So the area that corresponds to raw scores from 70 to 120 is 97.59%. I could have asked the same question here by asking what percent of scores were between a z of -3 and a z of +2, because that would have required me to shade and add the exact same regions, because remember, the raw scores have corresponding z-scores. You can use the method of sketch, shade, and solve to find the area between any two z-scores on the normal curve. You can also use this to find the area between any two raw scores by first converting the raw score to a z-score and then solving for the corresponding area. So far, we've seen cases where it's easy to chart them out on this curve. However, there are going to be some cases where it's harder for us to deduce this just using these simple percentages. For example, let's say we were trying to find the area from a z of 0.5 to the mean. Your first instinct after sketching and shading, as I've done here, might be to take 34.13% and divide it in half to get the corresponding segment that's highlighted. However, this doesn't yield for us the right number because the shape is sloping, and that causes our highlighted segment to not be the exact same area as the non-highlighted segment from 0 to 1. So we can't just take that 34.13% and divide it by 2 because these two segments to the left and to the right of our 0.5 line are not the same size. Instead, we must turn to a table that has charted out for us the exact area from any z-score to the mean or from any z-score to the tail. So for this, we need to turn to a z-score percent table. Here's an example of a page from a z-score table. You might also see these called critical values tables because they're typically in that section of a textbook or handout from your instructor. The first column in each row gives you the z-score. So you'll see this repeating in a lot of books to save space. The second column tells you the area from that z-score to the mean. If you look at the little doodles of a normal curve on top of each of these three column sets, you'll see that I've highlighted the area in orange that corresponds. The last section in each one tells you the area from that specific z-score out to the corresponding tail. And I'll highlight that again in the little drawings of the graphs above each table. Let's say, for example, that I wanted to know the area from a z of 0.7 to the mean. Well, I'm going to keep going till I locate that z of 0.7, and then I'm going to look for the area that corresponds from there to the mean. I see that corresponding to my z of 0.7 is an area to the mean of 0.2580. Now this is in decimal form, so if I want to convert it to percent form, I just have to move the decimal place over 2, and that gives me 25.80%. What if I wanted to know the area from a z of 0.7 out to its tail? Well, then I would look in the tail region of my chart, and that tells me that 24.20% of the area of the curve is from a z of 0.7 out to its tail. Now, you'll notice here is if I add the area from any z to the mean and that z to its tail, it'll always come up as 50% because what we're doing is taking 1/2 of the graph and dividing it into segments. Let's try this again with a more familiar segment of our normal curve. Pause here and see if you can use this table to find the area from a z of 1 to the mean. I've located my z of 1. Now I'm looking for the area to the mean, which it says is 34.13 or 34.13% if we translate it from the decimal form. It also tells me that the area from there to the tail is 15.87%. If I add these two together, I'm going to get a total of 50. That'll happen for all of these segments when divided from the mean to the tail. Now that 34.13% should be pretty familiar to you because we already sketched that out on the curves earlier today. Let's try again, but this time find the area from a z of 1.5 to the mean. I start by locating my z of 1.5, and now I'm looking at the area to the mean. The area to the mean is 0.4332. That's the same as 43.32%. If I had been asking for the area from a z of 1.5 to its tail, I would have yielded there 6.68% by looking it up in the table. Now take a moment to practice 3 of these on your own. Using the table here, find the area from a z of 1.25 to the tail, then from a z of 1.10 to the mean, and finally from a z of negative 1.10 to the mean. I recommend that you sketch, shade, then solve. Pause the show here and hit play when you're ready to check your answers. Let's start with the first one. I was looking for the area from a z of 1.25 to the tail. So I started by sketching the normal curve, then I drew in the line that corresponded to approximately a 1.25, and then I shaded in that area going from there to the tail. I'm then going to look at my z-score table to find the corresponding z-score of 1.25. Now specifically, I'm looking for the area from here to the tail, not the area to the mean. When I look this up in the table, I see that that corresponding percentage is 10.56%. So my area going from 1.25 to the tail is 10.56%. Following the same process, I move on to the second question, which was to find the area from a z of 1.1 to the mean. Well, I sketched and I drew my line at approximately 1.1. Now I'm going to shade in the area that I'm looking for. Now that I've done that, I'm going to look up the corresponding area in the chart. I see that the z of 1.1 has a corresponding area from there to the mean of 36.43, and to the tail is 13.57, but I'm not looking for the area to the tail. So that means that the area that corresponds to 1.10 to the mean is 36.43%. I'm going to try this one more time for the third example. We want the area from a z of negative 1.10 to the mean. I'm going to start by sketching. Now I'm going to shade. I've shaded my area going from negative approximately 1.10 on my sketch to the mean. Now when I look this up in the table, I notice that there is an area for 1.10, but there's no negative sign in front of it. This is because the graph is symmetrical. The area from a negative 1.1 to the mean is the same as the area from a 1.1 to the mean. So I'm still using from 1.1 to the mean, and my corresponding region here is going to be 36.43%. That's because my graphs are symmetrical. The area from negative 1.1 to the mean is the same as the area from 1.1 to the mean, because if you flip my graph over like a pancake, you're going to get the same area to the left or to the right. So the best way to solve is to always sketch and shade first. That'll help you identify whether you're looking for an area towards the mean or towards the tail, and then you use the graph by looking up z in absolute value. Now we're going to step it up a little. This time, pause to find the area between a z of 1.95 and a z of 2.65, using sketch, shade, then solve. This one's a little more complicated, but let's start with our sketch and shade. I've sketched and drawn in two lines this time, one corresponding to a z of 1.95 and another corresponding to a z of 2.65. I'm looking for the area between them, so that's exactly what I'm going to shade. I'm looking for the area above a 1.95 up to a 2.65. Now, nowhere in my table does it give me the area between these two locations, but it does give me the area from each of these locations to the mean. So let's start by looking at those. The area for a z of 1.95 to the mean is 47.44%. So I can fill that in my chart. That's the segment from the z of 0 to the z of 1.96. The area from a z of 2.65 to the mean is 49.60%. So that means I know everything from that line all the way to the mean corresponds to 49.60%. But I don't want to know that whole segment. I want to know just this segment between the two lines. So pause here and see if you can figure out how to find that mystery area. What you should notice is that if this whole thing is 49.60, and we know the part we are not interested in is 47.44, then we can delete the 47.44 or subtract it from the total 49.60 to get the missing segment. When I subtract, I get 49.60 minus 47.44 equals 2.16. So that missing mystery percent is 2.16%. That means the area between 1.95 and 2.65 is equal to 2.16%. Now we'll switch it up a little. This time, let's find the area between a z of negative 1.95 and a z of 2.65. Use the 3 steps: sketch, shade, then solve. Now that I've sketched and shaded, I can see I'm looking for a really large percentage because almost all of my graph is colored in. So let's start by finding our area that goes from a negative 1.95 to the mean. Well, I don't have negatives on my chart, but I know that the area from any 1.95, positive or negative, to the mean is 47.44%. I know that because I looked it up in my chart, and that's the percentage that corresponds to the area to the mean. So I'm just going to fill that in, 47.44%. So now I've figured out one of the two portions that I'm looking for, the area from 1.96 to the mean, but I'm still left with this other segment from the mean going to 2.65 to the mean. So I'm going to look that up in the table, and I see that area is noted as being 49.60%. This shouldn't be surprising because we just found these two areas a moment ago. But this time I'm looking for the total of these two areas added together rather than these areas subtracted from one another. So I need to add these two areas to find the total area from a negative 1.95 to a positive 2.65. When I add, I get 97.04%. So the area between a z of negative 1.95 and positive 2.65 is 97.04%. Now notice when we sketched and shaded, we saw that a really large portion of our graph was colored in. And now I'm getting that that corresponds to about 97%. So that makes sense to me. I colored most of the graph in, and it's telling me that's a very large percentage, nearly 100%. So visually and mathematically, things are aligning. So let's summarize how we can find the area between any two z-scores. To find the area between a negative z and a positive z, start by finding the area of each of those z-scores to the mean. Then add those two areas together. Now, if we're trying to find the area between any two z-scores which are on the same side of the mean, our steps are going to be a little bit different. That means if I'm trying to find the area between two positive z-scores, or if I'm trying to find the area between two negative z-scores. We start off the same way. We find the area from each z-score to the mean. But our second step is to subtract the smaller percent from the larger percent. So subtract little area from big area. This will give you the area between two positive z-scores or the area between two negative z-scores. The reason we're always going to subtract the smaller percentage from the larger percentage is because we can't end up with a negative percent when we're talking about real area under the curve.